This video is for topic 7.4, calculating the equilibrium constant. The objective for this topic is to calculate K based on experimental observations of concentration or pressures at equilibrium. So what we're going to do is we are going to start by practicing writing our equilibrium constant expressions. Eventually, we'll use these expressions to calculate K.
When we write equilibrium constant expressions, these are going to look very similar to rate laws. So we're going to treat them as if they're elementary reactions like we'd do with a rate law. So that means the coefficients become the exponents. And so it's always going to do, we're always going to do products divided by reactants. So basically the rate reverse divided by the rate going forward. So for our first one, for A, our equilibrium constant expression would be K equals, and we're going to do our products first, so concentration of NH3 squared, because it has a 2 coefficient, divided by the concentration of N2 multiplied by the concentration of H2 cubed, because H2 has a coefficient of 3. Okay, and then for our second one, we're going to do the same thing. So we'll do our products. So concentration of HCO3 minus 1, no coefficient, times H3O plus 1, also no coefficient on that one, so we have no superscripts, divided by concentration of H2CO3, no coefficient, so no superscript on that one either. We do not include pure liquids or pure solids in our equilibrium expression, so we're not going to include water in our equilibrium expression. Now, for the first one, for A, since these are all gases, it would actually be very likely, it doesn't specify in the question, that we would be looking at pressure, so Kp. So in that case, we would be looking at the pressure of NH3 squared divided by the pressure of N2 times the pressure of H2 cubed. So if you're working with gases, you can use it in terms of partial pressures. If you're working with solutions, you can write your K in terms of concentration. So this question has us looking at the reaction between aqueous iron 3 ions reacting with iodide ions to produce iron 2 ions and triiodide ions. So we're given the initial concentrations of iron 3 and iodide ions, so before the reactions happened. So that would be if they were in separate containers before you mix them. And then the reaction happens, and at equilibrium, we're told what the concentration of the triiodide ions are. And then the question asks us to find the value of Kc, so our equilibrium constant in terms of concentration. So we're going to use what are called ice tables. So we're going to look at how our concentrations are going to be at the beginning, and then how they change, and then how they are at equilibrium. So that's the ICE. So each letter is a row. And I just use the reaction equation as kind of my template. So I'm told my initial concentration of my iron 3 ions are 0.200 molar. And the initial concentration of my iodide ions is 0.300 molar. Now, before the reaction, I'm not going to have any product, so those are going to be 0. Now, we know that these are going to change based on their stoichiometric coefficients. So in relation to each other, the iron 3 ion the concentration is going to decrease by 2x. So it has a 2 coefficient. It's going to decrease by some amount x. And it's going to be in a 2 to whatever ratio, depending on what you're comparing it to. The iodide ion is going to decrease by 3x because it has a coefficient of 3. And then my iron 2 ion is going to appear, so it's going to be a positive change by some factor 2x, and my triiodide is going to increase by some factor of x because it only has one, it does not have a coefficient. It's just a coefficient of 1. Okay, so now we're going to treat these as little mini equations going down each column. So at equilibrium, our concentration of iron 3 is going to be 0.200 minus 2x. At equilibrium, our concentration of iodide is going to be 0.300 minus 3x. Iron 2 is going to be 2x, and triiodide is going to be x. Now, we're told the concentration of triiodide at equilibrium. We're told in the question that it's 0.0866. So that tells us what x is. X is 0.0866. So this one's easy because then we can just substitute that value in for each of these. So that means my actual value of my iron 3 concentration is going to be 0.0268. So I plugged in 0.0866 for x. I'm going to do the same for my iodide ion, which is going to get me 0.0402. And then my iron 2 ion is going to be 0.1732. My triiodide is going to be 0.0866. So it's just taking that value that we're given in the question because it tells us what the equilibrium concentration is. That happens to be x. And so we can plug that into the rest of our values. Now we need to calculate our Kc, our equilibrium constant. So we're going to start by writing the equilibrium expression. So Kc equals, we're going to do our products. So concentration of iron 2 squared, because it has a 2 coefficient, times our concentration of triiodide ion, divided by our concentration of iron 3 ion cubed, or nope, not cubed, sorry, squared, there we go, multiplied by our iodide ion concentration cubed. That one gets cubed. Now these are the concentrations at equilibrium, which we found out from our ICE table. So we're going to go ahead and plug those numbers in. So I have 0.1732 for my equilibrium concentration of iron 2. That's going to be squared, times 0.0866, my equilibrium concentration of triiodide ion, divided by my equilibrium concentration of iron 3 squared, times my equilibrium concentration of iodide ion cubed. So then when I calculate that out, I get an equilibrium constant of 5.57 times 10 to the negative 4th. And there we are. That's our equilibrium constant. So that would be, it says, what is the value of Kc? That is our answer. We are looking at the decomposition of C6H10I2, which is diiodocyclohexane, into C6H10 and I2. And so this, we're told in the question that we dissolve 0.050 moles of our reactant in a solvent, and the total solution volume is 1 liter. So we can use that to find our concentration. Then when it comes to equilibrium, we're given the concentration of our I2 at that equilibrium, and then we want to calculate the equilibrium constant. So we're going to start with our ICE table. So initial change equilibrium. Our initial concentration of our reactant is going to be our moles, so 0.50 moles, divided by our number of liters, which is 1 liter. So that's easy. That tells us our initial concentration. Just going through the steps to make sure we didn't miss a piece though. So our initial concentration of our reactant is 0.050 molar. We have no products at the start of the reaction. we are going to lose some amount X of our reactant. It doesn't have a coefficient, so it's just X. And then our concentration is going to go up by X for each of our products. No coefficients on either of those, so just X. So at equilibrium, we're going to have 0.050 minus X for our reactant concentration and X for our product concentrations. Now it tells us in the question that the concentration of I2 at equilibrium is 0.035. So that tells us our value of X, so 0.035. So that also tells us our concentration of C6H10. And then if we plug that in for X, for our reactant concentration, we do 0.050 minus 0.035, and we get a concentration of 0.015 molar for our concentration at equilibrium of our reactant. Now, if we write our equilibrium constant expression, we're going to do the concentration of our products, so C6H10, raised to their coefficients. Neither of them have coefficients, so it's just to the 1, divided by the concentration at equilibrium of our reactants. There we go. And then we have our values at equilibrium, so we can just plug them in. So 0.035 times 0.035 divided by 0.015, and that gives us our Kc value of 0.082 as our equilibrium constant. So in this question, we're looking at 0.010 moles of N2O4 gas in a 2-liter flask at 200 degrees Celsius. It reaches equilibrium by decomposing into NO2. And at equilibrium, our concentration of N2O4 is 0.0042 molar. Then it asks us to calculate Kc for the following reaction. So even though this is a multiple choice question, we're still going to go through the same steps that we did before. So we're going to start with our ice table. So initial, change, equilibrium. Our initial concentration, we're given moles and volume. So our initial concentration is going to be 0.010 moles divided by 2 liters, which would be 0.005 molar. So that's our initial concentration of our reactant. We don't have any product to begin with, so that's 0. Our change, our reactant is going to go down by X. Our product is going to go up by 2X because it has a coefficient of 2. So then at equilibrium, our concentration of N2O4 is going to be 0.005 minus X. And our concentration of NO2 is going to be 2X. Now for this one, we're told what our concentration is at equilibrium for our N2O4. We're told that this equals 0.0042. So we need to figure out what X is. So 0.005 minus X equals 0.0042, which leaves us X equals, and I'm going to write this in scientific notation, 8 times 10 to the -4th, just instead of doing all the decimals. So that means our concentration of NO2 at equilibrium is going to be 2 times 8 times 10 to the -4th, which is equal to 0.0016. So my equilibrium expression, Kc, is going to be my concentration of my product, so NO2, raised to the coefficient, which is 2, so squared, divided by my concentration of my reactant, so N2O4. So this is at equilibrium, so my concentration at equilibrium of my NO2 is 0.0016, and that's going to be squared, divided by my concentration at equilibrium of my N2O4 is 0.0042, which gets me an equilibrium constant of 6.1 times 10 to the negative fourth, which is option B.